So I'm just going to quick review what we talked about last time. So we talked about quaternion algebras. So we consider a general field K. The characteristic of the field is not 2, sorry, both 0. And we have two invariant values A and B, both non-zero. And we can define a quaternion algebra over K as K adjoining two sort of non-commutative variables I and j, such that square of I is A, square of j is B, and ij equals negative after ji. It's always 4-dimensional, and right, and with spaces given by 1, I, j, and ij, normally we denote by little letter k. So this, in many references, is denoted by saying differently, a comma b over k. I don't know. So for this lecture, I'll just use dk maybe. The goal we set up for this lecture series is that we want to classify isomorphic classes of all quaternion algebras over Q. The way we do that is by some local to global or local and global crystal. So we want to understand first of all quaternion algebras over R and over other fields extending, including Q, namely QP. So then we move on to talk about this p-adic completion of Q, namely QP. So on Q, there's a p-adic evaluation, namely we can write an integer A as power p times something not divided by p. And the p-adic evaluation of this integer is just the exponent on p. And norm is the norm of A. So norm of A, p-adic norm of A is p to the negative p-adic evaluation of this integer A, which is p to the negative n. So then if A is more divided by p, the p-adic norm of A becomes much smaller. It's a little bit strange if you first time see it. So the key property we emphasize are the p-adic evaluation is the product of two integers, the p-adic will add up. And then if you take the sum of two p-adic evaluations, it's at least, sorry, if you take the p-adic evaluation of the sum, it's at least the minimum of the p-adic evaluation of each of the integers. And it's actually an integer if the two p-adic evaluations are different. So at the very end of last lecture, we defined that Cp to be the completion of Z with respect to the p-adic norm, which is defined up here. So now I can keep it up for a little bit. The reason that this is well defined is because a norm of A plus B is less equal to the map, or rather the sum of norm of A and norm of B. So we define the metric. For any metric space, we can define its completion. Well, let's somehow be explicit about what I mean by this completion. So here's my understanding of another interpretation of what it is. So my understanding of what an element in ZP is. So say A. This is called a p-adic integer. So my understanding. So I'm going to give three understandings of a p-adic integer. So the first understanding of a p-adic integer is a sequence of integers. See, by definition, it's going to take completion. So that means you're taking all the closest sequences modulo their sort of equivalence relations. So a p-adic integer would be a sequence of integers that merge under the p-adic metric. And what I mean by converge, I mean that I can take things so that the an is congruent to an plus 1 modulo p to the n. What this would mean is that this would imply that if you take the difference between an plus 1 and an, if you take the corresponding p-adic norm, you know the difference will be divided by p to the n, and therefore the corresponding valuation will be greater than equal to n and the corresponding p lower will be less than or equal to p to the negative n. And as n gets larger and larger, this number is actually extremely small. It goes exponentially small. So this sequence will converge. So I can further, when you have this convergent sequence, you can define the p-adic evaluation originally defined over z or over q. You can now define it for the sequence by just sort of taking the limit of the p-adic evaluation. And moreover, because of this sort of stronger inequality, you can actually show that this limit stabilizes if the limit is not zero. If it's zero, then this limit will kind of go to zero in the usual sense. But if the limit is not zero, then we'll stabilize at some point. We'll keep repeating the same number. It was just really kind of reaching the limit in the final step. This first version of a p-adic integer, what it means to say a p-adic integer. It's basically by definition. Now I can take a small variant of this. Namely, I don't really have to kind of think about integers. In some sense, I don't have to know the precise integers. I just need to know what they look like modulo primes, power of p's. Sorry, modulo power of p's. So I can say a p-adic integer is again a sequence. So for A1 of congruence classes. Let's spell it wrong. So for A1, I don't remember its sort of integer value. I only remember what it looks like modulo p. And for A2, I think of this as an element of z mod pz. And think of this as an element of z mod p squared z. And the next one as an element in z mod p2. And go on. In the sense I just need to know what they are modulo p to the n. And there are obvious sort of reduction maps. Mod p squared go in this direction. And what we're requiring is that an plus 1, an is, for example, a2 is given by a3 modulo p squared. So this is going to be an plus 1 modulo to the n. So there's a sort of a concise way of writing everything, expressing what I just said. That was taking Zp to be the so-called inverse limit of n of the z mod. So it's just taking a sequence of elements in these groups such that they're sort of compatible under the maps. Yes?
I'm so sorry, we can't see what's behind the computer.
What? Is this?
Yeah. Thank you.
Such that by n is the fancy way of writing this is Zp is written as inverse limit of z mod p to the n z. Okay. So finally, let's just make it super explicit. I would really want to kind of sequence is not easy to work with. So there's something called a p-adic expansion. And also, it's somehow the sequence over here is not so very unique. Maybe two sequences will give you the same number. And over here, okay, it kind of will get unique because this will be somehow you will know what this number looks like modulo p to the n. And so you want to kind of put them together for all the information is right to the following to a. A p-adic expansion of a p-adic integer is just write like this, where these ai's belong to 0, 1, all the way to p. So for example, p equals 5, I can go like some number a equals 2 plus 3 times 5 plus, I can skip 1, which is where the 0, so and then skip along and keep going. So that's a 5-adic number, for example. So this is explicitly what in some sense, a p-adic number looks like. You can't really, somehow you have to, it might be a little bit counterintuitive in the sense that, okay, you can add, and you realize this number gets really big, and gets bigger actually much faster than you think. But this kind of converge in some weird way. The point is you have to think that if it's highly divided by 5, this is considered very small, although the usual absolute value is very large. Okay. So I'm gonna. I was gonna actually wanted to, but then I won't have the time. So I would say this as a fact that if an integer b such that p does not divide b, then b is actually invertible in ZP. Namely, in ZP, you can find an inverse of b. The easiest way to see this is that you can see using version 2. Namely, you know what a looks like modulo p. Excuse me, you know what b looks like modulo p. And then you can always find another b prime, such that b times b prime is common to 1 mod p. So you know what the inverse of b looks like mod p. And you do it mod p squared. Because again, p does not divide b, so you can invert b modulo p prime. And then you know the inverse of b looks like modulo p prime, p squared, and then keep doing. So this will tell you that Zp must contain all the rational numbers where as long as p does not divide b. So if you want to sort of periodically complete Q, you first of all periodically complete Z. But then you realize that after you periodically complete Z, you already include these prime to p integers in the denominator. So you just need to take care of the denominator of p. So just basically invert p in it. And it's also the same in the fraction field. So this is a little bit. That's what QP or what ZP looks like, and why this is somehow useful. I want to say that it's actually very easy to work with, and you can do a lot. You can solve this somehow if you want to solve some equations on this ZP or QP. It's actually a lot easier than solving it over the rational numbers. The reason is that you have this very useful theorem about hands-up level. I'm not going to study right now, but let's just do an example to get a feel of what it says. So let's say I want to find the square root of 2 in Z7. This is unthinkable over the rational because root of 2 is not rational. But when you complete with respect to a p-adic topology, it turns out you can actually get a square root of 2 in Z7. So how do I do that? So let me remark that using the same method, we can show that every integer that's not divided by p has an inverse, has an inverse, multiplicative inverse in Z. So let's do this. So the step 1 is we want to solve with square root 2. Well, we want to solve x squared common to 2 modulo 7. We do it mod 7, and the next one we're going to do mod 49. So solve this, and it's clear that x must be common to 3 or 4 mod 7. Right? At this point, I need to make a choice. So let me just for the rest of the construction, I want to make a choice. For example, 3. And we know that if I have found one of the square root, and the other square root will be the inverse of it. So I just need to find one, and the other one give it to me for free. Okay, so that's done. Step 2. I want to solve x squared common to 2 mod 49. This is a lot harder than solving mod 7, because mod 7 you can just enumerate. So go from x equals 0, 1, 2, 3 all the way to 6 and check the square of which one is common to 2. And for 49, that's going to take a lot more time. So we don't do that. What do we know? We know that x is common to 3 mod 7. So we'll use that fact. So we only consider those x's which are already common to 3 mod 7. So then the x looks like 3 plus 7y. I don't consider other possibilities. So if we had originally made the choice of x common to 4 mod 7, I would start with x equals 4 plus 7. At some point, we'll have to kind of make a choice and start on this argument. So I'm trying to solve this congruence of this 3 plus 7y squared congruence to 2 mod 49. So yeah, this is a computation you have to do. You have to multiply out. There's no good way. Right? And then when you square this out, here's kind of a small miracle that this term, this correct term, this is our most difficult term, has a 49 in front of it. But we're solving modulo 49. So it doesn't really matter what it is, because modulo 49, this goes away. So this suddenly becomes a linear equation instead of a quadratic equation. So let's move things around. Okay, let's see. Move 2 on the other side, how about that? So 7 plus 42y comes to 0, log 49. Right? Now all the terms here are divided by 7, so I divide by 7. So when you divide by 7, you don't really need to be common to 0 mod 49, you just get mod 7. Everything is already divided by 7. So y is common to 1 mod 7. This will mean that yx, if you go back here, kind of we only require y to come to 1 mod 7. But here I multiply by 7. So the 7y, we know what it looks like modulo 49. So, because I multiply by 7, the congruence will kind of multiply. Mod. So that's how you solve it. And then Step 3, then you want to solve it for mod 7 cubed. If you want to know what that is. 347, 43. Doesn't matter. It's some number. And what you want to do is that, again, you don't want the cube thing, the square thing. So what you want to do is you want to take x to be equal to 10 plus 49 times c. And then repeat the same argument. And when you square this, the term involving the square of z will be divided by, I think this time, 7 to the 4th. Now, when you modulo 7 cubed, it's going to go away, and then it becomes a linear equation which you know how to solve. So that's how you get the square root of 2 in Z7. To formalize, are there any questions about the procedure? So using this, you can you can write that as 7 plus this, and then whatever you compute here, and then just add 7 squared times that number. Yeah, if you want to actually write down the number, that's, yeah, I mean, yeah. It's something that can be only done by computer because the numbers are large. But the point there exists such a thing. You can always find such numbers. I mean, on the other hand, you're not supposed to. This is some number that cannot stop at some point. If it stops, then it must be integer. We know no integer square is 2. It must keep going. So, and there should not be some sort of periodic numbers. Otherwise, it would probably be some fraction number. So there's no. I know you can't really write it down. You can only write down the first, several terms, and then write down that term. That's it. You can do. And what I just said can be generalized to the following. Here's the following generalization of what I said. So consider any polynomial equation with ZP coefficient. And so that's somehow what we started out like. Just think of x squared minus 2. And then consider its reduction modulo p. Then we take all the coefficients and mod p. In our example, just x squared minus 2, we didn't change anything. But there's a condition for this to work. Our procedure, if you think about what really happened, is that we start out, we kind of pick a solution of this polynomial modulo p, namely x equals 3. And then we kind of keep producing it 3 plus 7, and then the next step is plus 7 squared times something, and keep going. Eventually producing a square root of 2 in Z7. I'm going to do the same thing. Suppose that R of a bar is a, suppose that the reduction is not 0. Otherwise, I could divide the polynomial by p. And I'll work with the thing divided by p. Right? So I just don't want a 0 polynomial. It's non-zero. And alpha bar is a simple 0. Of the reduction. Just we had in our early example, 2 zeros, 3 and 4. They are both simple zeros, no repeated zeros. If there were repeated zeros, they will fail. Then, can't see. Go to the other side. And the same argument as before, we produce a 0 in the PI numbers. Of your polynomial f. And of course, the relation between this alpha and alpha bar is that if you take alpha modulo p, you get alpha bar. Okay. Just like before, what you do is that you know what alpha should look like modulo p, and you pick an arbitrary list of alpha bar to modulo p squared, and you look at alpha bar plus p times y, and solve that. You're going to get a linear equation in y and then solve that. And next time you add another p squared z and you solve that. You keep doing, and then eventually you get a PI number. Are there any questions? Yes.
But this wouldn't necessarily work for like the intersection of two polynamials, like that G, the intersection of their two zero sets. You can do this at the same time. So you use the closest to one polynomial. Alright.
Sorry, how come about that?
Yeah.
It's not clear that it's going to work.
I don't think it will, but I'm just wondering if like are the conditions given on that G that for you to do this? This
I don't
being
know. I'll have to think about it. It's a good question. I don't know.
So in the same vein, are there multivariate equations?
That's just a question. Yes.
Yeah, as long as you have a smooth point on a variety of things. Any number of variables. You might have more than one list.
So you want a point to be a smooth one.
If you have a smooth point, then you have a whole dimensions worth of vector space worth of lists. So if it's a zero-dimensional algebraic set, then you have a unique constant.
That's right.
You
Actually,
just write down the Jacobian matrix instead of, so you have a whole bunch of linear equations you have to solve. And if that matrix is invertible, you just repeat the thing you said. You just don't do it one y at a time. You have a vector of y's.
Yeah. Well, I mean, that's the case when the equation is the same as number of variables. This is when the number of equations is equal to the number of variables. We can talk about that later. Actually, in one of your exercises, I put a kind of question. Related to that. Anyways, are there other questions? Yes.
Why does it matter that alpha bar is a simple
Because it's not true if it's not simple zero. For example, for Q2, we want to solve x squared minus 2 equals 0. This has no solution. For modulo 2, this equation reads x squared equals 0. Definitely has a 0, 0. But this one doesn't have a 0 in Q2. Basically, if you look at the sort of two-adding values of x, I mean, it's always an integer. But so therefore, the two-adding values of x squared must be an even number. But the two-adding value of 2 is 1. So they can't be equal. So there's no solution. Other questions? All right. Good. So now, we're going to use this tensor lemma. I want to determine the structure of the multiplicator group of QP. I mean, it's a field, so it's just QP leaving 0. I'm going to do it for PR. When P is 2, it's always a little bit weird. So if you go to a math conference, many people will declare that 2 is not a prime. So, anyways, 2 is always become a little bit different. Okay, so now let's do PR for each element that's not 0 in QP. I can always uniquely write this A as a power P, which takes out a kind of evaluation of A, or let's see how A is divisible by P times another U, such that 4. And an integer and U belongs to ZP, and the p-adic evaluation of U is 0. And this actually implies, as a fact that I won't have time to explain, but it's actually invertible in ZP. So the same thing as what I said earlier, that if P does not divide U, when U is an integer, then U is invertible in ZP. Similarly, if a p-adic integer is not divided by P, then it's also invertible. So with this, I can therefore write QP cross as just reading all this n, and the other part is invertible element in ZP. The map we get is you have a pair n and u, you send it to p to the n times. So that's the first step of analyzing the quantitative group of QP. Namely, you first pull out the valuation, and then there's a part which is p-adic integer and not divided by p. Now I have to analyze this bit here. Let's see where do I want to. So if you have a p-adic integer, just like integer, I mean, the idea is working with p-adic integer, you just think of it as thick integers. And you can do modulo p, and you get to z mod pz. Plus.
That first one is that first part is supposed to be
Yeah.